Thank you for invitation, by the way. And well, I'm talking about RISC, a compiler for parallel SystemC with maximum standard compliance. And my story starts a little higher level than the details that will come later. I was very optimistic in the past, and I thought, oh, here's my copyright permission slide for everybody. I was thinking that we can actually change the standard and to make all these problems go away. I've seen people working inside of it, outside of things, and making things and work. All these solutions are great, but the real problem, in my opinion, is the standard itself. So for standard compliant parallel SystemC, we have a big problem, which is the standard itself. And the standard is just a standard, it's not a law. We could change it. So this thing stands in the way of parallel SystemC. We have seen it all, and we can work around it with different things. But there's problems in the way. And back in 2016, so it's a bunch of years ago, I went to the Accellera SystemC Evolution Day, and I told the community what's wrong with the standard. I was hopeful, optimistic that the standard could change. It didn't happen so far and probably will never. So we need to work around it. But let me point out and what we really should do, and I will not stop talking about this. I think the standard should evolve and we should majorly change things. This is an ancient slide. You see the spider webs already on it from 2016. This is obstacle number one, and that's the biggest one. We have all seen it before. You all know it. It's the coroutine semantics, where we need to assume that things are running without interruption. That guarantee is something that breaks all our parallel hopes and makes it difficult, and we need to then catch or either prevent concurrent accesses and so on. Again, the real solution would be to change the standard such that we allow threads parallel execution, but there's an alternative, and the one that I'm selling, or not selling, but that I'm offering today, is to actually do this statically by use of a SystemC compiler. We can analyze SystemC code at compile time, and we can prevent parallel access conflicts. That's what our infrastructure does. And I'll show you right after these obstacle slides. The second obstacle that we have is the simulator state. There's things in the standard that actually really are DES, discrete event simulation. They are not prepared for any parallelism, and that need to be changed if we run things in parallel. Again, I would say this is still true. Even in 2016, I was asking for reviewing these primitives like SC pending activity that is in the standard. I don't know how you're working around these things. You're probably ignoring it in most of these systems, but that needs to change if we want to do parallel SystemC really. And I think that still needs to be done and can actually be done if we find a better semantics for it. The third obstacle that we identified was the lack of thread safety. You all are aware of that as well. And it's not just in the implementation that we need to be multi-thread safe. So it's not just the proof of concept simulator that we need to change. We also need to change the standards to really make things in parallel. There's these constructs that are inherently subject to race conditions, like these context ideas in the SystemC standard, that need to go away, and since 2016 hasn't changed, I still would impose that this needs to be changed, and we should change the standard there to not have these things in the way of parallel SystemC. There's an obstacle number 4. At that time, it was a big deal. We found that the SC channel is not different from the SC module. I think we agree that computational communication are a big deal to be distinguished. And there's an easy fix for this, and actually has been implied or has been proposed several times in the standard or in the standard implementation, that we distinguish channels from modules, distinguish communication from computation, and that is a simple change in the implementation. And also in the standard, we need to have this. We cannot have them the same type. We should actually distinguish them so that we can then safely communicate inside of channels. That can be fixed rather easily, and we did this in our implementation exactly that way. The TLM 2.0 standard at that time, it was new, and I didn't fully understand it. I will admit that. Nowadays, we do understand it, and my proposal that I made at that time to actually reuse channels in this context, that was wrong. I admit I was wrong in that case. So I would say my proposal is not right. We should actually, and we can use a compiler to actually ensure safety, even in TLM 2.0 communications with these speed transport calls and so on. That can be analyzed, and we did this. I had a student working on this, and we have one proposed solution for this. But details are beyond this 20 minutes that I have allocated. Sixth obstacle is the sequential mindset. Well, I put a strong title on the top to wake people up at that time. I don't want to accuse people that we are only sequential thinking. I see the community thinking about parallelism very well, so that is all good. But the technical aspect here was the SC method, which was methods are running sequentially, right? And not like SC threads. I was proposing at that time to eliminate SC method. That was too radical, and I don't think that's right. Today, I know better. SC methods are just fine, and the compiler can take care of them just like and can convert them automatically into an SC threads and convert it that way. So yes, the right thing I said is we need to have a parallel mindset. We need to think in parallel. We need to solve these problems. And given that even after all these years, we are still talking about parallelism and the obstacles there, I think that's what we want. We want an evolution of SystemC. Maybe even a revolution. We can be more aggressive if it's up to me. Last but not least, there's obstacle 7. That's the temporal decoupling. And as actually mentioned before in one of the talks that is there, we need to talk about it. There's the global time quantum, which is a single item in the parallel world of the SC threads and so on. We haven't gotten to it. I still would call this a future work item. But I strongly believe that compiler analysis can help here as well. But I cannot claim it right now. We haven't done it yet. That would be there. So let's remove these ancient slides. Let's go to the solution that we have been working since then, when we discovered that the SystemC standard did not change. It hasn't changed, and I'm not sure, I'm not holding my breath for it to be changed. We decided in my group to make the best of it, and we tried a different approach in context with the previous talks. We wanted to use a compiler, and we wanted to simply take SystemC as it is, most of it, build a parallel simulator, and put next to it a dedicated compiler so that we can comply with the standard as to the maximum extent. We created this RISC infrastructure, and we didn't know really where it will lead. We called it Recoding Infrastructure for SystemC. We wanted to just create technology that helps us parallelize SystemC and simulate it efficiently. And eventually we came down to two things. We have a SystemC compiler, a dedicated one that understands SystemC itself. And we have a SystemC simulator, something like the parallel simulators that you all have as well, and we know to modify those things. They can overcome those obstacles mostly, and I will describe that briefly to you. So our RISC system consists of mainly a compiler and a simulator, and we build a big software stack. It's this recoding infrastructure is just a software library with tools in it. We built on C++ Foundation, obviously. We borrowed a compiler infrastructure from Lawrence Livermore National Laboratories. They have a compiler that had source code analysis and source-to-source transformation capabilities built in. And based on that, which is a C++ compiler, we then made it SystemC aware. So we put a class hierarchy on top of all these classes that exist there for the compiler to understand what a SystemC thread is, what a SystemC module is. The compiler needs to be aware if we want to analyze these things and needs to know where there's the threads, where's the methods, and so on. On top of that, we then created a data structure, our segment graph, that actually identifies where there's potential for conflicts. Those are segments as a segment of code instructions that is there. And based on this data structure, we can then perform conflict analysis. That analysis is the basics. We have seen in the previous talks the same way. We need to find read-write, write-write, and write-read conflicts as before. It's the same situation. it's a basic compiler task that is there. So in our case, we have a compiler. It is then SystemC aware. We can build a segment graph. It looks in this gimmick here just as a high level, almost like a control flow graph, but it's different. It utilizes the segments that are in between all those wait calls, where we actually have scheduler calls into SystemC caller, into the SystemC kernel, I shall say. And these segments then may or may not conflict with each other. We need to analyze that in this in our compiler, and we find out for every segment where it is reading, where is it writing from, and we do this statically. So in contrast to some of the previous talks which do this dynamically, they catch it at runtime, we try to look at the code and identify potential conflicts there. And potential conflicts is obviously more than the actual conflict, so we need to be conservative here, but whenever there's a potential for two segments to access the same piece of memory, the same variables there, in this example here, the variable x that is being written by two segments, then we will prevent them from running ever in parallel and simply mark them as forbidden or as conflicting with each other. And once we do this analysis, every segment against every other segment, and we be conservative, we can create a table, and actually multiple tables in the details of this situation, where we mark these conflicts in a table and pass this information then back into the model, which we create automatically with this compiler. We create a parallel C++ model that has this information and that therefore is safe from all these conflicts. We pass that then to the simulator, and the simulator makes the decisions at runtime based on the tables that we stick into the model, and can then run things in parallel that are safe, and will run things sequentially that need to be running sequentially. So with that, we get safe execution. We keep the SystemC semantics of these uninterrupted execution of these segments, and we gain maximum parallelism with what is allowed by the standard at this point. We gain fast simulation there. I don't want to waste time to go into further details here. I will share a few results with it. We have many in the literature, but this is my favorite slide, where we used a highly parallel platform, the Intel Xeon Phi coprocessor system, on a highly parallel application. I admit that it's a Mandelbrot renderer is embarrassingly parallel, but this shows the potential that is there. And when it goes through the compiler and the simulator can make runtime decisions, we can get high speed up in multi-threading, basically. So if we have on a core 60-core machine here, we can get to 50 times speed up in that sense. And if we put SIMD, basically in data level parallelism next to it, we get another 7x of it. So in total, we can gain up to 200 times speed up. And that is really impressive. I always thought this is tasty enough for the industry to jump on it and try generate the energy to even attack the standard and so on. But that hasn't happened yet. So with this compiler and this setup, we can get a high level of speed up, and we can do things mostly standard compliant. We have this available in the public domain. We have a release 063 at this point, and there's technical reports, lots of documentation, as well as a Docker image available, so you can play with it easily. The link is on the slide. You can go there, play with our system, and actually run your SystemC models and compile them with the compiler, and then run them as fast as the system allows. In conclusion, we have this recoding infrastructure for SystemC. There's a compiler, a dedicated SystemC compiler, and that's different from all the other approaches that we have seen before. Our compiler understands SystemC and therefore can analyze it. We do this then with a parallel simulation engine, very similar to the other approaches on many core hosts, and we do it even out of order parallel. An important point that I heard before is that there's actually very few threads that are running at the very same time that you parallelize. We need to do things a little bit out of order, temporal decoupling, whatever, and that we agree with. We have our own way for doing this as well. And we try to aim with this SystemC standard in maximum compliance. But generally, I think as an academic researcher, there should also be a way to go to a better SystemC, to a revolution of this. Anyways, with this approach, we can overcome those obstacles that we identified back in 2016. And I need to thank Intel Corporation. They sponsored much of this work significantly for this. So thank you for this. I have a few more acknowledgements to my group here, obviously, and collaborators in Intel and so on. And I provide for reference later some references for publications that are there. But I'm looking forward to discussion now. And I see that I'm almost out of time. So this is a good way to stop at this point. Thanks. And I'll be happy to answer questions.
Thanks a lot, Rainer. Thanks a lot.